use XR, the XR formula. Look. Now I'm going to look at, for whatever n is, I will look at the period that consists of years 1, 2 through n, where everything starts now. So at the beginning of the whole thing, when r is equal to 0, then of course you are just starting. There is nothing that has happened before. So the only thing that happens at that time is the investment. So, excuse me, x0 is always equal to minus p0. Important for this project. So raise your hand if you agree with that. I didn't see any hands. You know, keep in mind, you know, there are people that would die for being able to raise their hands but they don't have hands. And you have two hands in good shape and you don't raise any. Huh? So what I was saying is that at the beginning, nothing of this exists. So the only thing that really exists is the initial investment. So x0 is equal to minus p0. And I was saying, I was asking to raise your hand if you agree with that. Now, I believe in redemption. I want to give you a possibility, an opportunity to redeem yourself. You know, it's one of the most, redemption, next time you think about it, redemption is one of the most beautiful words in all languages. In Spanish, I can teach Spanish a little bit for free. It's called redención. It's a beautiful word, redención, redemption. Okay. Now, this is the assumption I'm going to make, that I make the investment at the beginning and no more investments for the rest of the period. So for r equal 1 through n, then xr is equal to all this, and when I hit this one, this should be equal to 0. Okay, the other thing I want to make, let me, if you don't mind, look, I'm going to do this. N minus 1. Let's make that. Because when you have the last one, when r equal n, then x of n should be equal to all this, in minus c n minus r n minus c n minus b n times 3 minus 0. But at this time you get the salvage value, remember. You get the salvage value at the end. See, I did not make this totally clear in my PowerPoint presentation, but I do say it there. This is a more clear way to see it. Okay, now I will appreciate it if you help me with the lights off now. See, I'm making you burn more calories. Huh? Okay, here it is. Look. And then now the formula looks really like this. x0 plus x1, you bring 1, divide by 1 plus I to bring it to the present, and then x2, you divide by 1 plus I squared, and so on, and the last one, xn, you divide by 1 plus I to the power n, and bring it to the present, and set that equal to 0, and the whole idea is to get the value of I. And we are going to use straight line depreciation, which means that P0, the initial investment, minus the salvage value divided by n, that is going to be equal to D1, D2 to Dn, and where P0 is the initial investment. Okay, the procedure is this. Variables I, C, and T for the calculation of x0 are 0 here. That's what I said. Okay? Yeah.
Dr. Garcia, can you go back to the salvage value? That's just some random constant, is that correct?
Yeah, the salvage value is a constant.
I mean, it's not, you don't know what it is, you just put it in there as a placeholder right now?
Okay, the salvage value, we need to get a value for the salvage. Remember, we are going to get data for our calculation from simulation.
Mm-hmm.
So once you simulate the value of P0, your initial investment, then you simulate a value for the salvage value, and then you do the subtraction, and this n also comes from a simulation. And then for this particular run of the simulation process, then you calculate D as P0 minus L over N for all the years in that planning period. I have the intermediate result, so you can follow that. So all these are zero, so initially we have just this one, and for what I did here is the number one, the number two comment here, comment number two, and here we are going to start simulating one operation, or one investment, if you will. So first, you simulate N, P0, and L. And then, using these values, you determine D. And then you generate, since you simulated N, then you generate N sets of values for I, for C, and T to calculate X1 through Xn. And remember, variables I, C, and T for the calculation of X0 are zero, just like I said here, because this is the initial state before any time has passed. Also, P1 through Pn, here I have it, they are zero, no additional investments. And once these Xn plus 1 terms, you have Xn plus 1 term, look, you have N here and one at the beginning, N plus 1, then you can use it. You can write the rate of return equation, and then you solve it. Okay. To generate an empirical distribution of I values, then we can repeat this several times, because you would like to have like a histogram for the I value once you do the simulation many times. See, in general, one simulation run helps very little, because I'm going to just show you one simulation run. But to gain more insight into the quantity or quantities that you are trying to understand, then you simulate them out many, many times. So let's generate one trial. Okay, I got tag numbers 22, 69, and 33 for N, P0, and L. That means 5, 1 million here, and 100,000 there. That's now, since this is equal 5, then I need to generate X0, X1, X2, X3, X4, and X5. And in X5 I have a little note here saying that it includes the salvage value like I did here. Okay, then I have to have tag values for I, and for C, and for T. So let's say X0 is equal to minus 1 million, is the same value that I have here. X1, then I got it, the tag value was 14, that actually corresponds to 700,000. Then I got another tag for C, which is 66, corresponds to 200,000. And for T, I got a tag value of 15, corresponds to 50%. And when I do all these calculations, then I get 340,000. That's the way to get this one. Then to get also tax values 98, 31, and 42 for I, C, and T respectively, and you get A 50,000, 150,000, and 52%, and then you calculate the cash flow equal to 4020.6K, 429,600, and you continue with X3, X4, and X5, and for X5, to calculate this 529,600, then remember that you need to include the value of L, which is 100,000. So that was equal to 429.6 plus this 100. That gives you 629,600. Excuse me, 529,600. So that's where the bulk of the effort is, to put it together this table. When we have that table there, then I can write this. I have my formula now there. Look. And then I can use the Newton-Raphson method. It's one of the procedures. There are other methods. The bisection method is also a method that's very good. But using a numerical analysis procedure, then you can get that the answer is about 28.15%. And then as an exercise, don't do it now, but just for you to practice, just try with this. and get this, I'll give you those tag numbers, and you practice with this, and remember that the last one must include L. Okay, now, these are the 6 problems that happen every time, every day in Operation Research. Okay. They are inventory processes, allocation processes. We are interested in the second one more than in any other one. QN processes, replacement processes, competitive processes, sequencing processes. You have the 6 or that. Competitive processes use something that is called game theory. That's what it's referred to as game theory applications. I am going to describe these 3, and as an exercise, I want you to read the description of this from the reading guide, so that I won't bore you to death with all these descriptions. But when I give you the quiz, and see, my quiz could be describe the replacement process. That's all. Things like that. Very simple thing. I don't expect from me anything that unreasonable. I'm going to talk about the inventory processes. In inventory processes, there are 2 sources. Or maybe there is a source for some item. It could be a service. Okay, there is a source for one particular item. That item can be either ordered or it can be manufactured. So there are 2 ways to get your items: producing them or ordering them. In general, without going into details, the rate of replenishment is finite when you manufacture the items. And the rate of return is infinite. It's an instantaneous thing. When you order the thing and you get it. I am ignoring at this time to describe this application and the delay time between the time that you order and the time that you get the stuff. The simplest case is a situation where you order instead of producing it. And remember, I'm not going into the math of this. I just want to describe the process so you understand what is a manufacturing process, an inventory process. So there are 2 ways: you manufacture the item, or you order the item, and that's done according to a replenishment rate. And then you have a source of items here available. And then at the end, on the other side, you have a demand that you need to satisfy. And the demand that you satisfy happens at a rate too. So there are 2 rates here. One is the rate of replenishment, and the other one is the rate of demand satisfaction. And an inventory problem really is how to match those 2 rates to minimize cost. Okay? So when in general you have a rate here which is D units per time unit. Okay? Now, in here, when the sources come to you, when the items are taken from the source, is at a rate of P units per time unit. So now here it goes, if this go at a rate of D units per time out, and this come at a rate of P units per time in, then this must be less than this, otherwise you will never have an inventory. So here you have a rate of replenishment, and here you have a rate of demand, and as a result of the 2 rates you have an inventory level. And you have cost for everything. You have a fixed cost for ordering. You have a cost for holding the item in inventory, and things like that. In the reading guide, I have a lengthier description of the same problem. But in general, the inventory problem has to do with how do you balance these 2 rates in such a way that you will have a minimum cost in the total operation. so no math, just an idea. I hope you would. Somebody asked you, what is an inventory process? Just think about that. The two rates, and that they need to balance them, and you balance the rates in such a way that you will minimize all relevant costs. Relevant costs are the cost of ordering. Every time that you order, that's a fixed cost. Every time that you set up a manufacturing process, there is a fixed cost. Then there comes the cost itself of the item. And then when you have an inventory, there is a cost of an inventory cost. And then how do you minimize all these costs? You don't want to have less items than you need. You don't want to have more items than you need, and so on. So there are a lot of entire courses and books on inventory systems. But we are not going to study inventory systems at this time. But I just want you to have an idea about recurring processes in operation research. So I want you to educate yourself a little bit. If somebody says operation research is cannot be applied, it's nothing, then I want you to be able to say, oh, no, there are at least six recurring problems in operation research. 3 days ago, my son showed me the list of the best jobs in the United States for 2016. Okay, I think the first three are dentist, orthodox, and nurses, the area of top, computer scientists and computer analysts is number 3. And when you go down the list, number 19, operations research analyst. Number 19, operations research analyst. A lot of people in the industry are looking for people who know operations research, who really know operations research, not that can talk about operations research, people who can solve significant problems and make companies help companies make money. Number 19. Number 18 was a statistician and a data analyst. Down the list, I was greatly satisfied to see that he was a university professor. And I thought to myself, I've been a lucky guy, you know. I have been a university professor for 40 years already. I said, you cannot ask more than that. And I feel blessed by having all of you as my students. I mean it. Okay. So what can I ask? Can I ask myself? You know, good health.
Kinological mind.
Yes. And so lots of steak on the grill and Colombian coffee. I intend, before I have to go, I intend to take care of many cows. Okay, the allocation problem, this is our problem. Let's say you have one resource, I call it resource 1. This is particularly important to us. And another resource, at this time let's start with 2 resources. And I'm calling the black resource and the red resource. And we are going to perform some activities are represented by green boxes. Activity 1, activity 2, and activity 3. Okay, what are we talking about? Let's simplify the situation. Let's say that you are in the business of selling windows and doors and tables. Window frames, or windows and doors and tables. 3 things. What do you need to do those 3 things? You need wood, that's resource number 1. And let's say that the other one, there are more resources, but let's say that the second resource that you need is machine time. You need to use some machines. There is a third resource that will be labor. Well, I'm going to have only 2 resources just to simplify our life. Okay, then the activities consume resources, but the activities give you money, give you a return. So here, this picture is very clear. You are taking from resource 1, and the activities are taken from resource 2. And the quantities taken by the activities are A11, A12, and A13 for resource 1. Okay. Notice that the first subscript is 1 all the time. That 1 corresponds to resource 1. And the second one corresponds to the activity. So what does it mean? It means the following thing, that if the activity is set at a level equal to 1, so that could be 1 door, or it could be 1 table, or it could be 1 window frame, then the wood meter will be given by this in pounds of wood. This is data. Similarly, for the second one, machine time, we will take A21, A22, and A23. In here, I color this. You see that the second value here, second subject is blue in all cases. So this is a blue 1, a blue 2, and a blue 3. This is a blue 1, a blue 2, and a blue 3. That's for the activity. And this one, the first one is black 1, and black 1 for resource 1. And this is red 2, and red 2 for resource 2. When you give the power presentation to yourself, then you will be able to see the colors better than here. And the level of activity, how many frame, window frame, how many doors, how many tables, they are represented by X1, X2, and X3. And those are the values that I want to know. The rest is data. Okay, now let's say resource 1 and resource M. In general, you have M resources. And the amount of resource 1 is B1. The amount of resource 2 is 2. B2 is the available amount of each resource, B1, B2 through Bm. And then, let's see, these numbers are the same. Well, I'm going to represent now the consumption of the resources as functions of the activity levels, the X's. See? This is the first formula that I actually give you in this class. That is very relevant to us. Let's look at this. Sum for j equal 1 through n. Okay, j equal 1 through n are the activities. Before in my picture before I have j equal 1, 2, 3. So here I have n activities. And I equal 1 through m means m resources. So I have n activities and m resources. The level of activity j is x of j, so it will be x1, x2, x3 through xn. And these are the a's of ij values that I mentioned to you. Okay, now what does it mean? It says the total consumption of a resource I should not exceed the maximum amount available of that resource. That's what it means in English. Now, this is total consumption because what? Because I have added together the consumption of that resource for every activity. Because the counter here, the summation is j. Okay. So if, let's say resource, the first resource, I equal 1, then I equal 1 here. So it will be A1 times x1. Second one will be A12 times x2. The third one is plus A13 times x3 and so on. That at the end is less than or equal to B1, which is the quantity. Can you understand that? Can you visualize that? Okay. Now what is the measure effectiveness? Cost, profit, etc. Activity 1, activity 2, activity 3, and then each activity has to have a contribution into the measure effectiveness, into the cost, into the profit, and so on. Now, what is the contribution for one unit of the activity? When the activity level is set equal to 1, then the contribution of that activity is C1. When the activity level for the second activity is 1, then the contribution will be C2. That's data. And the other one will be C3. And then we set the levels X1, X2, and X3. Those are the decision variables. We want to know the values of the X's. So in this case, you have C1, X1, C2, X2, C3, X3, and we put them together, and then we have this objective function that you minimize or maximize. In this case, if it is profit, you maximize. If it is cost, you minimize. You know, the total contribution of all the activities into the measure of effectiveness. Usually the measure of effectiveness, the sum, is called the objective function. And the value or the name of the objective function usually is Z. We use the value Z, the letter Z. So what do we want to do? We want to optimize the measure of effectiveness subject to the resource constraints. Okay, what are the resource constraints? These are the resource constraints. So we want to optimize the measure of effectiveness. So what is the measure of effectiveness? C1x1 plus C2x2 so far, and so on, up to Cn times xn. You want to minimize or maximize that, subject to this constraint. Okay. We are going to investigate this problem in this class more than any other problem. And we will make some assumptions. Now the third process, the last one I will describe today, and then you read the description of the other three, is the QM process. Almost all problems in businesses and in industries of many kinds can be actually viewed as QM processes. You think about it, it's very, because in a lot of situations you have a kind of a probabilistic behavior of the system. Okay? So a lot of problems can be viewed really as one of the 6 recurrent problems in operation research. The inventory problem, the allocation problem, now the queuing problem or queuing process. Okay, in the queuing process, we have an input source that we call population, and that input source provides customers, and the customers in queuing terminology are called arrivals. So from the input source, customers arrive and join a queuing system, and the queuing system has 2 components. One is the queue itself, and the other one is the service mechanism. When I was a student, an undergraduate student, our professor told us something that is really true. It's human nature. He says, these customers are upset because they are not in the queuing system. But once you are in the queuing system, you are less upset. You know, when you are get your dental checkup or your medical checkup every year, and when you are outside with everybody, you get a little bit mad. Don't get too mad because they are going to take your blood pressure, remember. So, and they are going to take a little bit of your blood. And if you get unhappy at that time, trust me, things are going to go up. Bad things go up and good things go down just because you got upset. And you start thinking negative, and you start getting a little bit worried, and so on. The body, I don't know, is unforgiving. I have tested that on me. I'm an expert in that kind of stuff. I know. I checked it. So they will measure your blood, and once you get out, you know, you cannot change that blood. It's there in that tube over there. We have a lot of those things, have the angry, have the frustration, the thing that you were thinking about. So when you go to the doctor next time, you wish all the time. Protect that sample of blood with your life to get good things there. You follow what I'm talking about? Yeah. Okay, so like my professor used to say that when you are here, you are upset, but once they put you inside, it's when the nurse comes and says, come with me, and they measure you and take you high, and they make you wait 30 minutes there. You don't worry too much because you are in already. So many people know that, and they ask you to join the queue here. Well, what the heck, you are in the queue. But they are, you get much better when you are in the service mechanism, like when the doctor is checking your reports and everything, or whatever, you are being tested. Same thing with services. So, the customers arrive at the queue, then from the queue go to the service mechanism, and from the service mechanism go out as served customers. So there are, in particular, two rates again. One here is the rate of arrival, and this is the service completions. Okay. This is the number of arrivals that come per hour or per minute or per unit of time, and this is the number of customers served per unit of time. So you have customers arriving at a rate and customers being served at another rate. Again, the arrival, the rate of arrival is a little bit larger than this one. That's why you have a queue. And then you go into the service mechanism. There are many things regarding this process. For example, there is something that's called the discipline of the process. That's the rule that they follow to take people from the queue into the service mechanism. One is, for example, first in, first out. That seems to be the fair one, but sometimes it's first in, last out, and so on. So there are a lot of things, service disciplines, we call them. And so a queuing process is really the way you balance the rate of arrival with the rate of service completions. It's similar in a way to the inventory learning, you know. So, and there are costs involved here and so on. The service mechanism could be a single unit, or it could consist of multiple units in parallel. There are many, many possibilities. Yeah. The same thing with the queues. You could have one queue for several servers, or each server may have its own queue, and so on. So there are many problems that can be described as queuing processes. And then you know the good course on probability is the best for this. And then once you have a good course on probability, then a good course on something called stochastic processes. Stochastic processes endows you with a lot of knowledge to deal with these queuing systems. So as an exercise, you can check all the other processes in the reading guide. Okay, now I finished the first topic. Let me introduce to the second topic. It's an introduction. So really, this is the beginning of our class in some ways. The first topic, the purpose of the first topic was kind of to motivate the importance of operations research, and in particular to make you aware of the scope of operations research, and so that in your mind you will think that operations research is something worth learning. So we are going to discuss linear programming problems for half of the class. Probably has a little bit more. I'm going to provide you with an introduction, the assumptions of linear programming. Linear programming is referred to as LP, formulation and graphical solution of LP problems. And then after we go through the graphical solution, we go into the general mathematical model for the LP problems and introduce two terms, canonical and standard forms for the LP model. That's what I intend to do in the first topic, in the second topic, I'm sorry. Okay, first, as an introduction, let's read this. It says, many people rank the development of linear programming among the most important scientific advances of the mid-20th century. That's no exaggeration. Its impact since just 1950 has been extraordinary, nothing but extraordinary. Today it is a standard tool that has saved many thousands or millions of dollars for companies or businesses or even moderate-sized in the industrialized countries of the world. Today, an OR analyst is number 19 in the list of best jobs in the United States. This is the picture, it is a photograph of George Bernard Danzig. He was born in 1914 and he died in 2005. He was from Oregon. He was born in Portland, Oregon. He is the father of linear programming, and he is the inventor of the simplex method, the procedure that we are going to learn. So we are trying to get into the head of this man. That's what we are going to do. He was born November 8, 1914 in Portland, Oregon, to Tobias and Anja Danzig. And he passed away on May 13, 2005 at the age of 90. That's a good age to go, 90. He's the father of linear programming and inventor of the simplex method. And this is an anecdote, is very well known in the OR world. He was a graduate student in Berkeley, and one day he arrived late to Jerzy Neymann's class on probability. This guy is extremely well known, one of the biggest in statistical, in probability theory. So he went, he arrived late, and then he saw some stuff like I have written here. He copied it down because he thought that was a homework assignment. And when he went back and told Jerzy Neymann's, he gave it a homework, he said, "Oh my God, you just solved a problem that had been unsolved up to now." So I say that because the guy was a genius. Yeah. He got his BA from Maryland in 1936 and a master's degree from Michigan in 1937. And he got his PhD from the University of California at Berkeley, and he was a professor in Stanford University until his death. He was professor of OR and computer science. He got the von Neumann Prize from the Operation Research Society and the Institute of Management Science in 1975. This ORSA Teams thing doesn't exist anymore. It was put together as something we call INFORMS, the Institute for OR and Management Sciences. He was the recipient of the National Medal of Science in 1975. He also was a member of the American Academy of Arts and Sciences. These two are very distinguished, the National Academy of Engineering and the National Academy of Sciences. And he wrote his classical book, Linear Programming and Extensions. Okay, he was a great credit to the human race. Okay, now here, I'm going to go back to the problem that I was discussing before. You have these activities, and you have all these resources, and those activities perform something and give you an output. And the output is going to be measured. The output, like for example, this may be tables, window frames, doors, and so on. Okay, but you cannot add apples to oranges. Then you need to re-express these outputs into a common unit. Many times that's dollars. But you can think about the profit. So you put all the outputs of the activities into a common unit and put them together, add them together, and you have the measure effectiveness. Let's say you have resource 1 and resource 2, and this activity 1, activity 2, activity 3, you have here. This is the same picture I had before, look. Those are the amounts of resource consumed by 1 unit of each activity, or when the level of activity is equal to 1. And the levels of the activity are going to be x1, x2, and x3. And here you have these 2 resources. And you have the same formula I had before. Now, the amount consumed for resource 1 will be A11 x1, A12 times x2 for the second activity, and A13 times x3 for the third activity. For the second one, the same thing, but it will be, the only thing that changes is the first subscript, look. And now we are going to put them together here and here. And then we are going to say that they are less than or equal to B1 and less than or equal to B2. Now I'm using kind of longhand notation for the same thing that I had used, presented before, using a compact notation, the summation sign. Remember. So you have resource 1 and resource M. So in this case you have M resources. So this is the same formula I showed before. And the measure effectiveness is similar. 3, C1, C2, and C3 are the contributions of the activities into the measure effectiveness per unit of activity. When the levels are equal to 1, but we want to find levels x1, x2, and x3. And then into the measure effectiveness we have C1, x1 from the first one, C2, x2 from the second one, and C3, x3 from the third one, and then you put them together, and then you have that one. And then let's look at some of the assumptions of the linear programming. Okay, let's look at this one, for example. Okay, that assumption is a pretty important one. If the contribution for x1 is equal to 1 is C1, then the total contribution when the activity is set at x1 should be C1 x1. Okay, so notice that no matter what the level of activity is, the contribution of the activity is always the contribution per 1 unit of level times the activity level. Okay, that is called proportionality. Proportionality. Okay, let's give you an idea about when proportionality doesn't satisfy. There are situations in real life where proportionality is not true. Okay, give me some ideas. For example, suppose that you are manufacturing a particular item, and if you might manufacture 100,000 units, can you say that the cost per unit is always the same as when you manufacture, for example, 10,000? In many situations, not in all, in many situations, there are something that we call economies of scale. And when you have economy of scale, you don't have proportionality. But there are many problems where you do have proportionality. Okay, this is proportionality. Now, this second property or assumption of linear programming is that if you want the total contribution from the system, what you have to do is to add individual contributions from the components. See, in other words, there are no gains, no losses when you put them together. There are situations where there are gains and losses, and there are problems where you have gains and losses. And here you don't have that happening. So this is called additivity. So we have proportionality and additivity. And proportionality and additivity together are called linearity. And that's why we call this linear problem, or linear problem. So you have proportionality there and additivity. Now let's look at this. This is for the objective function. Here the same thing, okay? Let's look at this, I think it's better. Here, look, for any resource, you know, the resource when the level is 1 is A11. When the level is X1 is still the 1 per 1 unit times the number of units in the level. And if you want the total consumption of the resource, then you add it. So here you have proportionality, 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 and you have additivity. So you have proportionality and additivity both in the objective function and in the constraints. The constraints are the resource consumption quantities, and the measure effectiveness is the objective function, or could be the profit, could be a cost, and could be other things. So one is proportionality. The output and the usage of each resource are directly proportional to the level of each activity. Additivity. Given any activity levels, the total usage of each resource and the resulting total measure of effectiveness equal the sum of the corresponding quantities generated by each activity conducted by itself. Now the third one is divisibility. Divisibility means the following thing, that the activity level doesn't need to be a whole number. It could be a fractional number. That's what it means, divisibility. Because you could, let's say that to facilitate the presentation of this thing, let's say that you are, the activity levels represent quantities that you measure in kilograms. So you can have an activity level at 100.50 kilograms. But if the activity level were to make automobiles, you cannot make 100.50 automobiles. So in that case, that will not be a linear problem because the divisibility assumption will be violated. So activity units can be divided into fractional levels so that non-integer values for the decision variables, which are the levels of the activities, are permissible. And the other fourth assumption is certainty. Certainty means that all the parameters, all the data are fixed values. When it says the input is 3, it's 3, it's not 3.1, it's not 3.05, it's 3. And that has some limitations because in real life, those numbers may vary a little bit here and there. But anyway, all models are imperfect. But many models are very useful. Okay, so George Box, an outstanding man in the field of design of experiments. I mean, you have taken design of experiments. I teach design of experiments, and I have taught it to I think one of the cohorts in the past. But George Box, who was professor at the University of Wisconsin, he was a British, an Englishman. He used to say, fondly, he says, all models are wrong. And that is true, all models are wrong. Because no model represents anything perfectly. But he never said that all models are not useful. Models are very useful. Okay. Bax was married to Fisher's daughter. He had pedigree. And Sir Ronald A. Fisher is the father of the design of experiments. From England himself, and he was a knight. was Sir Ronald Fisher, and Fisher's daughter was married to Box, to George Box. So the final, so there are four main assumptions. The last one, 5, the fifth one, is that the activity levels are always non-negative. I'm telling you this right now. The real assumption of linear programming are 1, 2, 3, 4. So the fifth one is for the convenience of solving the problem, because we are going to use the simplex method developed by Danzig. And then the simplex method can be used only when the variables are non-negative. So we will stick in there this fifth assumption. Okay, I'm going to finish here. It's 3 o'clock. So I am going to give you a quiz through this today. Maybe 2 or 3 short questions. I mean, a week from today. 2 or 3 questions. Okay? Very fair questions. See, notice that I have taught A, B, C. So I'm going to ask you A, B, C. I have not taught you A, B, C, and I'm going to ask you X, Y, Z. Some people do, but not me. You know? So make sure that you know your ABCs. And I'll see you a week from today. Have a great weekend. Yeah.
What about our homework?
Homework. Okay, homework. You can solve the problem, the homework individually or in groups of 2. You choose another person yourself. You choose a person you feel comfortable working with. And I'm going to send the homework. When I send a homework, I'm going to send one this weekend, so you can start cracking away, because you know I don't want you to be restless during the weekend.
So you'll send one?
I'm going to add minimum to your weekend. So
And
you,
then we'll turn it in.
then I will put it in Blackboard in a folder that's called assignments, and in that statement of the homework I will give complete information of what you have to do. Okay? You will send the homework since it is a practical way is if you send me a file with the solution to the homework.
Email.
Yeah, via email.